This time I will be talking about convolutional networks for text. I think this is a really good tool to have in your toolbox when you want to be modeling things. So I'll try to explain kind of the basics of it. So the example problem where I think convolutional networks have been most successful and kind of are definitely the standard is sentence classification. So of course this is the example that I've shown before where we have the I hate this movie, I love this movie, etc. And the one approach that you can do to doing this is the bag of words, where you calculate the scores for each of the words, add them together, and get a bias, and make scores to get probabilities. But it's also very easy to come up with examples that break this, like I talked about before. So for example, I don't love this movie. There's nothing I don't love about this movie are examples where that would break this. So we talked about continuous bag of words, but this basically still has the same problem. This doesn't consider word ordering at all. It doesn't consider word co-occurrence at all. So it can't even take into account that you have the word not in love in the same sentence. And then we talked about deep continuous bag of words, where basically we take all of these, add together, run them through non-linearities to extract combination features, and use them for prediction. And in this case, our vectors can represent things like feature combinations. Feature 1 and 5 are active, or capture things like not and hate exists somewhere in the sentence. But what it can't handle is the fact that not and hate appeared directly consecutive to each other. Obviously, positional information, because language isn't just a bag of words, is important. And it'd be nice to have a way to capture this. So one way to handle combinations is a bag of n-grams. And a bag of n-grams, basically what you do is, instead of looking up bags of words, you look up all of the length n sequences up to say 3, for example, in this example. And you look up individual vectors or scores for each of these, and you use these for classification. So you could add all of these together, get a bias, and get scores to calculate probabilities. And this is not a neural network at all, but this is a method that was used before neural networks came into prominence. And actually, this is a pretty efficient way to allow us to capture combination features like don't love or not the best. So these are, if these are very common in a reviews data set, for example, it's pretty easy to learn the patterns for these features. And especially if you have a limited number of classes, this is not such a bad thing. It also empirically works pretty well. So this is a thing from back in 2016, where a particular deep learning researcher released a data set for like automatic theorem proving. And they had an 83% accuracy baseline using neural networks or something. And then Haldo May, an NLP researcher, then about 1 hour later, calculated a bag of n-grams baseline using logistic regression, and got 85% accuracy with like 20 lines of Perl or something like that. So, these are not things to be laughed at. And one of the advantages is that these, bag of n-grams, you can train it quickly, easily over large-scale data. You don't necessarily need stochastic gradient descent. You can use like more stable batch learning methods. So it's certainly something that to be reckoned with, I guess. But it has problems. It has the same problems as all of our other, kind of discrete count-based models, like parameter explosion and no sharing between similar words and n-grams. So because of that, we use convolutional neural networks, which were covered in the reading. So One-dimensional convolutions, basically, which were also covered in the reading, what they do is you extract a vector, and then you calculate the same transformation over contiguous sequences of these vectors. So, you might take in the first and second vector, second and third vector, third and fourth vector. And basically, what this allows you to do is do soft n-gram extraction. So, if hate and dislike have very similar vectors, the features for I hate this movie and I dislike this movie that are extracted by this function and this function will be very similar, right? So this is kind of the advantage of using neural networks in these cases. And then you can put these into a combination function like a pooling function and take a softmax to get probabilities. So actually, believe it or not, these kind of networks were invented by Alex Weibel, who some people might know. He's a faculty member here. They were first used for speech recognition in 1989. And were empirically effective then, but like most neural networks in 1989, we didn't have the computational power to train them to do all the exciting things that they can do nowadays. Actually, I heard Alex Weibel give a talk once, and he said, our experiments in 1989 took 1 week, and our experiments in 2019 take 1 week. So like our significant experiments. So basically, the upper bound on the patience of researchers is about 1 week, and if you get any longer than that, then nothing is going to happen. So that's the only constant in our research, and it's the main limiting factor in our research. So the name convolutional networks was actually kind of coined later in the image processing domain, and was used for things like character recognition. And because of this, like a lot of our terminology comes from this. It comes from, like, we have convolutional filters, we have perceptive fields, we have all these things that are kind of inspired by vision. But in the end, the basic idea is the same. The idea is that we have a single computation, a single type of computation, but we sweep it over inputs, either in 1 dimension or in 2 dimensions, to extract like local features that are then combined together. So that's the kind of, I guess, background and history. And CNNs for text, actually, many of the methods for neural networks in the recent neural network boom started out with CNNs as their initial one. And Colbert and Weston, 2011, this is a journal article, but I think they had a conference paper in 1998 or something like this, which won the ICML Test of Time Award for kind of revolutionizing neural networks for NLP. Oh, sorry, 2000, yeah, maybe 2008 or something. So basically, it's generally based on 1D convolutions, but it often uses terminology or functions borrowed from image processing for the historical reasons. And there's kind of 2 major paradigms that you can use CNNs for. One is for context window modeling. So basically, this is if you want to do tagging or something like that, you want to calculate representations of single words, but dependent on the context around them. Or you can use it for sentence modeling, where you do convolution to extract n-grams, and then you pool them together to combine over the whole sentence. So I keep on talking about things like Elmo and Bert and other things like this. These are kind of things for expressing the context of words in sentences. And actually, Colbert and Weston also, were thinking about this in their original paper as well. And that's what the first thing is here. So just to give an overview of the architecture that they used for this, basically what it looked like is you had your input text, where you have a bunch of different features. I I think essentially they tried to only use word features, but in the end they gave in and used like part of speech features and other things to beat the state-of-the-art accuracy at the time. But essentially, this could either be a single set of features, or words and part of speech tags and other tags. You look these up in a lookup table like word embeddings. Then you run them through a linear. Let's see. Actually, sorry, the convolution isn't very easy to tell here. But I believe this is a convolution. Then they have a hard 10H non-linear activation function, and then they do it again. And then for sentence modeling, basically they have a similar thing where they look up the features, they do convolution, and then they do max pooling over time to get just the features. Run linear layer, hard 10H layer, linear layer, and do sentence classification. So you could kind of see that these could be used for both. Yeah. So then the kind of like standard function that you can use for convolutions, either in 2D space or just in 1D space, is it basically takes input and parameters, and the input, which is the things that you want to process convolution over, has rows. So for example, the rows could be words. It has columns. The columns could potentially be, if you're talking about an image, the rows and the columns could be like rows on the vertical, in the vertical domain, columns in the horizontal domain. And then you also have features. So if you're talking about an image, the features could be like 3 RGB features or something like that. In the case of text, it's a 1D convolution. So basically, you could have rows. Let's see. You can think about it in a number of ways, but you could either have like rows equal to the number of words in the sentence, or columns equal to the number of words in the sentence. And then the third dimension of your tensor is the size of the word representation. So this would be like 512 deep if you had word representations of 512. So you could see that unlike in an image where you have 2 dimensions, you could have only 1 dimension, because text generally only has 1 dimension. Another example of applying CNNs to sequences is if you're doing something like speech processing. And if you're doing speech processing, actually it makes sense to have 2D convolutions. Because, for example, this could be something like the frequency domain, and this could be the number of frames in speech. And frequency is kind of like a continuous, so you could think of like doing a sweep over both the frequency domain and the frames. But in the case of text, each individual dimension in a word embedding doesn't really have an order. Kind of like you could randomly permute the order and it would still more or less mean the same thing. So in this case, I think thinking of the features as channels is probably a more like natural way of thinking of things. Then you also have parameters, and the parameters are basically the width, or the number of rows, the number of columns, the number of input features, and the number of output features. So in the case of something like a 1D convolution over text, you might have the number of, let's say we're using this expression here, where the columns are equal to the number of words. So in this case, you would have maybe 1 row, because it's a 1-dimensional convolution, 3 columns, which means you're taking steps over 3 words at a time, and then 512 input features, if that's the size of your word embeddings, and then 1024 output features, where you want to extract like more features than you had in the input. So, so this is basically what this looks like. Depending on your library, you might not just have 2D convolutions. You might have 1D convolutions. You might have 1D wide convolutions, 1D narrow convolutions. You know, whatever. But basically, you know, all of these can be expressed as 2D convolutions, so it's often easier to just use this. Are there any questions about this so far? Yeah.
This might be a dumb question, but I'm wondering what decides the dimension of the convolution function. So if you L equals to 2, does it really represent 2 convolution function? Or it only depends on the input, like if it's text, then it's just one convolution.
So the dimension, I mean, you can be creative. You can come up with reasons why you would want to do 2D convolutions for text. One example of this I'll talk about later. But in general, yeah, text will be a 1D convolution, and like images or something would be a 2D convolution. You might have videos where you would want a 3D convolution, or things like this. So I think it's basically the dimensionality of the data that you have for your input. Yeah. Anything else? Okay. So there was a question about the types of like padding and narrow and wide convolutions. So after convolution, the rows and the columns of the output tensor can be larger or smaller or the same as they were before. So depending on what you want to do, the type of thing here will be different. So if you just want to extract, if you want to basically calculate context for particular words, then you will probably want the dimension to be the same. Like for example, let's say you want to do tagging of words. You want to do part of speech tagging. In this case, you'll have one vector for each input word, and you will also want one vector for each input word after you do the convolution as well. So this is sometimes called the same convolution. The easiest and most straightforward way to do this is to select a convolution window that's an odd number. So it could be, like 1. 1 is not very useful, but like 1 or 3 or 5 or 7 or something like that, which means you have an identical number of context on either side. So then if you have A, B, C, you calculate, let's say your context window is 3, you calculate using the vector for B, you calculate using the vector for A, and you calculate using a vector for like a padding symbol over here, where this like padding symbol can either be like a 0 vector, or it can be a special vector indicating that this is like your padding vector. So this allows you to ensure that after your convolution you have the same number of vectors in the output, which is good for things like that. For things like sentence classification, you have no such constraint, right? You can basically, one thing that you could do is you could say, okay, I'm just going to, like if we have A, B, C, D, we'll just take the ones that actually exist, and this will reduce the number of things in the output to be equal to the number of things in the input. So I think the question on Piazza was, what is the final number of vectors you have? And I think this is the number of inputs. So in this case it would be 4. This would be the number of outputs, and then you add 1 just because like if you look here, obviously you need to add 1 because filters will reduce the sellers. So then you get 4 minus 3 plus 1, which is equal to 2. Then I think this answers the question of Yazoo. I don't think it was a typo in the book. So, because yeah, this is the filter width. The filter width is 3, and the number of inputs is 4, and the number of outputs is.
Sorry.
Yeah.
I think the question you got is about the wide convolution of the narrow convolution.
Oh, wide. Oh, okay. I'm sorry. I briefly looked over it because I got it just before I came to class. But okay. So then, for the wide convolution, the output is basically what you do is you pad up to the size of the you pad up to the size of the filter minus 1. So if you have A, B, C, D, you also pad and pad and pad and pad. In the case that our filter width is 3, so then you get all of these things. So that's 1, 2, 3, 4, 5, 6, which is 4 plus 3 minus 1. So what's that type of book then? Okay. Yeah. So yeah, I'll email you off and complain. So yeah, so basically, intuitively, you can pick any of these. If you're doing something like text classification, I think a wide convolution kind of makes sense. And the reason why wide convolutions kind of make sense is because if you have A at the beginning of the sentence, that's also kind of a nice thing to know, right? Like, so if you have the word good at the beginning of the sentence, maybe that's different than having the word good at somewhere else in the sentence. So this kind of adding of the padding allows you to capture that easily. It's an auxiliary concern if you do narrow convolutions and you have a sentence that's shorter than your filter width, you start running into problems. So I personally don't use narrow convolutions very often, but you can use them if you want. Okay. So striding was also covered. I didn't get any questions about this, so I'll just go over it quickly. But basically, striding skips some of the outputs to reduce the length of the extracted feature vector. So if your stride is 1, then basically you move your window every first. So like every time you move the window forward by 1. If you have something like a stride of 2, instead of incrementing by 1 every time, you increment by 2 every time. So this allows you to skip, and this reduces the length of the final output vector. This is very, very useful if you want to do very long sequences, for example. So to give another example, if you're processing speech, or if you're processing like character by character, this is very, very widely used because speech has a bunch of frames, and each individual frame doesn't mean very much, but if you combine them together, you can kind of get more salient concepts. So in speech, it's very, very common to do some sort of striding to reduce the input to something that's 1/4 the size or 1/8 of the size before going on to do something like speech translation or something like that. Similarly, for character-based models, you might do strides to reduce the number of characters by 4 before you feed it onto a downstream task. So there was also a pooling. So pooling calculates some reduction of the functions feature-wise. Basically, actually, I don't know why I said it's like convolution. I must have written this 2 years ago. But like pooling, basically what it does is it's a way to reduce variably length sequences into more or less fixed length sequences. And the reason why this is important is if you want to do like text classification over variably length, sentences, you'll need a fixed length vector before you feed it into your final classifier, right? So the most common one is max pooling, which is essentially, did you see this feature anywhere in the range? So to give an example, like not great, did you see something like not great anywhere in the sentence? And if so, this is probably not a very good review, right? So that's what max pooling will allow you to do. Also, average pooling, how prevalent is the feature over the entire range? K-max pooling, did you see the feature up to K times? And dynamic pooling. So dynamic pooling is kind of interesting, and it's, I don't know, I feel like it's used in NLP sometimes, but it's not used very much in other, not used as much in other areas. But basically, it's, did you see a particular feature in the beginning of the sentence, in the middle of the sentence, or in the end of the sentence? So you split the sentence up into 3 parts, and you calculate the pooling over each of the 3 parts. So then if you see positive words in the beginning of the sentence, you can give them higher weight than seeing positive words in the end of the sentence. Yeah?
I actually have a question about dynamic pooling.
Sure.
All the examples in Robert's book, although it's the names, it's listing dynamic. The example given in the book are kind of an ad hoc segmentation of the sequence, basically using your domain knowledge. So has there been any work on like actually making it dynamically learning the structure, like the number of regions that you want to separate the sentences?
That's a good question. I don't know of anything like that. Usually my impression of dynamic pooling is the name is actually kind of deceptive, I think, because it's more like, I don't know,
It's like
segmental pooling or something like that. I don't know what better word I would come up with. But basically the idea is that you're pooling over particular segments, but usually the number of outputs you get is fixed, because then you use a fixed number of outputs downstream. So, yeah. Any other questions? Okay. Yeah.
If there is any best practices on how to select the number of headings in right convolution?
The number of what in the wide
Heading?
heading? Well, so wide convolution by definition has the filter width -1. That's kind of like the name, like the name wide convolution kind of implies that the heading is k-1 on either side. Yeah, I wouldn't overthink this. I think probably that's fine. But yeah. Yeah.
So is there any techniques to choose the number of filters? Because I think intuitively, a filter is like when you want to select a feature out of this sentence. So how do you choose the number of filters for this?
So how do you choose the number of filters? This kind of turns into the broader question of how do you choose the size of the hidden layers in any neural network? Because I think the convolutional filters are basically a hidden layer in a neural network. So you have the same question for MLPs, for regular like feed-forward networks. You have the same question for RNNs. I think the answer is essentially it's a hyperparameter. If it's too small, your model will not work very well. If it's too big, your model will probably still work okay. It'll just be slower, especially if you're using something like dropout. Even if you make your model too big, usually you don't overfit too badly. I should tell you one very interesting thing that might not be immediately obvious. This applies to all neural networks, not just convolutions. But it's even if theoretically your model could be learned with a smaller number of hidden layers, it works better often if you have a net that's too big. It's easier to learn. So an example of this is the XOR function. So a lot of people have, probably is an example of neural networks. You've seen, or you might have seen the XOR function, which looks like this, where basically you have +1, -1, +1, -1, +1. Actually, this might not be XOR. This might be like the opposite of XOR. But so you have you can't learn this with a linear classifier, right? But you can learn it with a neural network that has two nodes in its hidden layer, with 2 values in its hidden layer, theoretically. But if you actually tried to train a neural network with a hidden layer of size 2 to learn this, it only learns it about half the time. Because it falls into a bad local optimum where it picks essentially a linear classifier. However, if you take a neural network with a size of 50, with a hidden layer size of 50, it learns it every single time. It never, fails to learn. And I think the reason why is because neural networks are very highly, non-convex. They won't necessarily find something that's optimal for the problem. And there's actually kind of an interesting paper recently. Hang on one second. I'll pull it up. So this is the paper, and basically the idea is the neural networks. If you train a small neural network, and then if you train a small neural network, it won't learn as well as a big neural network. But the reason that they argue is the reason here is because some parts of the big neural network are initialized well and are able to learn the problem. So the parts of the neural network that are initialized well basically learn to solve the problem, while the other parts just do useless stuff. So you can then go back after you train the model, delete all the useless ones, and relearn the neural network, and it will learn to solve the problem just about as well. So in the XOR thing, basically what you would do is you would train a 50 hidden node neural network to solve XOR, find all the nodes that aren't helping to solve XOR, delete them, and then go back and retrain the network with the nodes that were actually useful, and that would solve the problem 100% of the time. So I think the interesting thing here is that essentially you probably want a bigger network because it's easier to learn, even if it's too big, as long as you can prevent overfitting with things like dropout. As long as you can fit it on your GPU, it doesn't take too long to train. It might be overkill at some point, but I think that's kind of the conclusion that a lot of people have had now. So, sorry, I went very long aside, but hopefully it was helpful.
Once we delete the useless nodes, why do we need to retrain it when the network works?
Oh, okay, yeah. So I'm sorry, I got a step ahead of myself. What you can also just prune away all the useless nodes and then use the smaller network as well. The easiest way to do this is to find the nodes that have very low weights in the weight matrix, and then just delete all of those. You can also just delete low weights in the weight matrix, ones that are close to 0, which does time and memory savings. So there's a bunch of neural network pruning techniques, and this paper has a lot of references to them if you're interested in looking more. So, yeah.
In general, how can you make out whether a node is useless or not? Because one of the things you generally monitor are the loss and accuracy or whatever.
So ones that have very low activations are an obvious thing. I actually don't remember exactly what they did in this paper to measure that. But in other papers, you can find ones that don't get big gradients, that don't contribute to the loss very much. If you delete them, they don't change the predictions very much. There's a bunch of different ways to do it. Yeah, any other questions? I welcome questions like this. I might go off in asides, but yeah.
I wonder, will optimize the value of the convolutional network after tuning will do similar things like sort of like a dropout things you mentioned?
Quantizing?
I mean, quantize the value after doing like so it's for the to save the memory, but like not much lose.
So this is something I definitely know exists. Like, you reduce the precision of the floating
I wonder
point.
whether they contribute in this similar way or like they're totally different directions.
Yeah, I don't know that. What I do know is that quantizing values for neural networks tends to hurt performance. You have to work to make it not hurt performance, and there are methods to do that. But I think that might be a bit different than things like dropout. So, yeah.
So to go back to the pooling,
Yeah.
So some of the paper you reference use like K-max pooling and dynamic K-max pooling. So what are the intuitions behind using which, essentially? Like when does it work best in what kind of NLP test?
So K-max, honestly, I don't think this is used very much anymore. It was the idea of why you would want to use K-max pooling is if you see an n-gram 3 times, that's probably more informative than only seeing it once, right? Like, let's say you wanted to do topic classification and you wanted to see how often you saw soccer-related terms. K-max pooling, what it would allow you to do is, instead of max pooling, which would say, did you see a soccer-related term just once? It would say, okay, you've seen it 3 times because all 3 of the values of the K-max pooling are high. Or if only one of the 3 values of the K-max pooling is high, then you'd only seen it once. I think it probably still is a useful thing to know, but as I said, I haven't seen it used that widely recently.
More useful for longer documents?
Would it be more useful for longer documents? Yes, it very well might be. Yeah.
Could you give examples of how dynamic pooling might be used in 2 cases? One, if the convolution pooling layers are near the inputs, and if they're farther away, how would you incorporate it?
How would you use dynamic pooling? How would you use dynamic pooling when the layers are near the inputs versus far away from the inputs? I don't think there's anything inherently different about those. I feel like it would be about the same. Once you use dynamic pooling once, then you essentially have a fixed size. So you probably wouldn't need to use it again. But yeah, I think no matter where you use it, basically the general idea of taking fixed segments, like a fixed number of segments where the size of the segment depends on the size of the input would be the same there. Yeah. Does that answer the question?
Could you give like a use case example for dynamic pooling? So where exactly do you use it and how would you use it?
Well, so a very simple example from text classification for dynamic pooling is if you want to take, let's say you have an output of size 4. What you would do is you would take an input of size 10 for one sentence, an input of size 20 for another sentence. And the dynamic pooling would then calculate over the first quarter of the vectors, the second quarter of the vectors, the third quarter of the vectors, and the fourth quarter of the vectors. And that would mean instead of doing like max pooling where you take the max over all of them, you would take the max over just a segment of the input. And the reason why that might be good is maybe the position where a word or n-gram occurs is important information for solving a task like classification. I'll actually have a few examples later that are maybe even better examples of why this would be useful. So maybe I can talk about that later.
But does this harm long-term dependencies in any way?
Does this help long-term dependencies in any way?
Segmenting and essentially between smaller segments.
Maybe I can talk about that after I talk about dilated convolutions also. So we have an example of a CNN-based classifier. that you could use. For stacked convolutions, this helps address the long-term dependency problem. So a stacked convolution, as it said in the book, is basically feeding in a convolution from previous layer results into a larger, which results in a larger area of focus for each. So in this case, you have convolutions of size 2, where the first layer of convolutions of size 2 is basically expressing bigrams, and then the second layer of convolutions of size 2 is expressing trigrams. But if you combine these together also with striding, let's say you have a width of 2 and a stride of 2, the first layer will basically be bigrams, but then the second layer would actually be 4 grams. And if you did this again, you could get 8 grams, and then you could get 16 grams. You could get 32 grams. So you see, the increase in the number of words that are covered by a stacked convolution basically it can be exponential in the number of layers, which is a nice thing to have. So there's a specific example of this called dilated convolution. The difference between dilated convolution and strided convolution is basically a dilated convolution is a strided convolution, except you, when you do the stride, you don't actually delete all the, so this, I'm sorry, this is not a very good, this figure is not a very good example of this. Let me, so this is a better example, a better figure. I'll have to fix the other figure. But basically, the way the dilated convolution works is you take one step at a time, and you move this blue filter, or this blue like series of convolutions one step forward at a time. And what this means is when you're calculating the features for T9, you would basically look back in time, an exponential number of steps. So in this case, you have 2 steps, 4 steps, 8 steps, 16 steps. And then when you move to T10, you just shift this 1 to the right. So you're still looking at 16 steps, but it's shifted 1 to the right. So essentially, what you can think of dilated convolutions as is they're basically strided convolutions, but you apply them in a way that you get the same number of vectors in as you got out. So the reason why this is good is you can use these for applications like language modeling or tagging or something like this, where you need to make predictions at each point. So for example, if you wanted to do language modeling on a character-based level, for example, you could do this strided convolution, dilated convolution, and you get vectors at the very top level that basically express this big space of lots and lots of characters in the past. And then you use this to predict the next character or next word. And this, in the paper that I just showed you, it's called Neural Machine Translation in Linear Time, proved to be a very effective way of doing character level prediction, because basically, if you do 6 layers of this, you get a history of 2 to the 6, which is actually this very, very long history. But you get it in a sublinear, a log number of connections in the network. So you don't have to face things like vanishing gradients or things like this that you would have to, that are a bigger problem when you're using RNN-based architectures. So yeah, this is also a nice thing to know Were there any questions about this? Yeah.
So this, it's every time step. What would we consider time step in terms of text?
So a time step could be like a word or a character or something like that. So it would be one elemental thing that you look up a embedding vector for. So in this case, it would be this would be time step 1, time step 2, time step 3, time step 4. Is that that answer? Okay. Anything else? Okay. So, whoops. So just to, I mentioned this a little bit before, but there's a few advantages and disadvantages to using these types of methods. In contrast to recurrent neural networks, which I'll be talking about in the next class, there are fewer steps from each input, so that could be a word or character, to the final representation that you'll be using to make a calculation. So for example, in a dilated convolution, as I said, basically from I, which is, let's see, 16 characters before, to the final vector here, you have 1, 2, 3, 4 steps. So you can see the number of steps is log n in the distance between the input and the output. However, if you wanted to use a recurrent neural network, basically what a recurrent neural network does is it takes one step at a time through this whole sequence. Then you would have to do 1, 2, 3, 4, 5, 6, all the way up to 16 steps. And the more steps you do, essentially the harder it is to train, or the harder it is to do credit assignment when you're doing backpropagation. So, another really big advantage of CNNs is each of the individual computations in a CNN is independent, in a particular layer of a CNN is independent of the others. So basically you're doing identical computations that you step one at a time over windows. And because of this, it's extremely easy to parallelize on GPUs. And if you have a GPU and run a convolution, it will end in no time compared to running a recurrent neural network. It'll just finish extremely quickly. And other hardware like TPUs, for example, that Google developed are even more, extreme in this. They're just made for doing these kind of things. One slight disadvantage of this is it's slightly less natural for handling kind of arbitrary long distance dependencies. And so an example of this would be if let's say we wanted to know whether the word tennis appeared anywhere previously in the document. So like if you wanted to know tennis, if you knew tennis appeared somewhere previously in the document, and it's a good indicator that the next word might be racket, for example. In RNN, basically the moment it sees tennis, it can activate a node, and it can keep that node forever. It can keep that node on forever, and this is a very simple operation for an RNN. For a dilated CNN, basically you would need to learn that if the node appeared in this segment or in this segment, that's an important node to have. Or if it appeared in this segment or this segment, that's an important node to have. And if it appeared in this segment or this segment, it would be an important node to have. So you need to essentially learn this at all layers, and you can't just like turn it on and keep it and keep this forever. So it's a little bit less natural in some ways for that. Also on CPU, CNNs tend to be a little bit slower. They have more computations that are a little bit harder to keep in cache memory, but it's not a huge, extremely significant difference. So yeah. One kind of interesting piece of work on this, which actually we had talked about at the LTI colloquium. So if people go to the LTI colloquium, you already heard about this earlier this year, but it's basically a method for sequence labeling called Iterated Dilated Convolutions. And the idea here is basically you have different widths of dilated convolutions that you use to calculate context. But instead of having separate parameters for each of them and having like the same stride for each of them, you have varying strides. And you also share parameters between different iterations of applying this here. So the idea is essentially like you move out to being able to calculate very wide context using wide kind of dilated convolutions, and then you move into local context to do this, and then you do this over and over again until you get your final representation. And empirically, this seems to work very well and also be very efficient. So are there any questions about this? Yeah.
So is there any empirical investigation of when RNNs can outperform CNNs or vice versa?
When RNNs can outperform CNNs? Yeah, I feel like I've read something like this, but I don't remember the paper name or like how to look it up. That's a really good question though. Let me try to find this and post it on Piazza or something like this. Or if does somebody know? Yeah, a good example.
Zico culture has a behavior.
Mm-hmm.
I'm not sure if it's the one that you refer to, but
So it actually talks in the opposite way when CNNs outperform RNNs.
When CNNs, so it's by Zico Coulter is.
there is one.
Okay, yeah. It was by him and what was the name of the first author?
Last name is by EAI.
Okay, yeah, I think that is the one that I was thinking about. So if you search for Zico Coulter, so yeah, that's a very good one. I think there's lots of individual investigations of this. So basically, like it's very common for somebody to propose a new architecture, and then compare like a CNN-based architecture that beats an RNN-based architecture, or an RNN-based architecture that beats a CNN-based architecture. But when you write a research paper about this, you have a very strong vested interest in your your method working better than other people's methods. So I don't tend to trust these as much as ones that are just trying to answer this question itself, and those tend to be a little bit more rare. But I think this one is a good example. My personal impression over reading lots and lots of papers is that CNNs tend to be very good for classification. And I think the reason why CNNs tend to be very good for classification is because basically bag of n-gram models are very strong methods for classification, because what you want to do is you want to find salient terms in the text, and then you want to basically identify the salient terms and then just use them to decide what class you want to assign. And that's exactly what CNN-based models are doing. RNN-based models, I feel, tend to be better for things like decoding in neural machine translation systems, or like language modeling or things like this. So if it's something where you want to predict like the next word or something like this, I feel like RNNs tend to be better. Whereas if you want to do classification over whole sequences, CNNs tend to be better. But I think it's not necessarily that clear cut. So, yeah. Anything else? Okay. So as an aside, an important feature of all neural networks is nonlinear functions. And the proper choice of the nonlinear function is essential, especially in stacked networks where you have very deep networks. Because if you make the network too deep and you have a nonlinear function that isn't good, it can lead to the gradients disappearing in the earlier sections of the network, et cetera. So like an obvious nonlinear function that we never use in neural networks is the step function. So the step function is 0 if the value of the input is less than 0, and 1 if the value of the input is more than 0. Why don't we use this in neural networks? Because it has 0 gradient, exactly. So almost everywhere it has a gradient of 0. So this is difficult. This is difficult to learn with gradient descent. So what we can do is we can smooth this into something like a tan h or a sigmoid function, which basically softens the step function, where you have a gradient where you have a strong gradient right close to 0 and a smaller gradient far away from 0. This also isn't usually the best function to use. Why is that?
You have 0 gradient on the parts far away from the origin.
You have 0 gradient in the parts far away from the origin. So this also has 0 gradient almost everywhere. When I say almost everywhere, the range of this function, or sorry, the domain of this function is plus infinity to minus infinity. But the gradient is 0 for almost the entirety of that domain. So basically, when you're using tan h, parameter initialization becomes very, very important, because if you have really large parameters that cause very large outputs, you get 0 gradients almost everywhere. These are very hard to train. So instead of this, it's common to have things like ReLU or soft plus or like all kinds of other things, where you essentially have a gradient that is non-zero for a large part of the input. So ReLU, basically what it is it's 0 if the value is if the input is less than 0 and the gradient is 1. It's the identity if the gradient is more than 0. Or sorry, if the input is more than 0. And soft plus is like a soft version of ReLU, and then there's a bunch of other things like this. My impression is that training with ReLU is a little bit less, it can explode sometimes. So tan h won't explode, but it might not learn, whereas ReLU will learn, but it might explode. So you get wildly increasing or decreasing loss functions. There's a ton of different activation functions that have been proposed in the literature, and like sigmoid, swish, maxsig, coside, minsin, arctid, max tan h, L, ReLU, like all these other things. And the question becomes, which do you use? Every paper that proposes a new activation function says it's the best activation function ever, of course. So, essentially, this paper very recently by Egger et al. 2018 did a whole bunch of tasks, and they measured which function was the best for all of these tasks. Essentially, they found that the standard methods worked pretty well. Like ReLU tan h worked pretty well. They found penalized tan h, which is this tan h function where you multiply it by 0.25 when the value is less than 0. I'm actually not super familiar with this, but it's a method they use here. They found that this seemed to work pretty well, but I think in general, ReLU and tan h are pretty good ones to use, and then you can try the other ones if you're interested.
Isn't it because it's just, they're more common, so they're more likely to have produced the winner, and more exotic stuff is less?
No. They tried all of the functions for all of these tasks, so it's a complete empirical comparison. Are there any questions about these things? Okay. Yeah, sir.
Does the choice of activation function affect the performance of the network significantly, or is it really only minor differences to the extent that's not really worth searching for different activation functions?
Does the choice of the activation function affect it significantly? I would say in combination with other hyperparameters, yes, it does. So like, for example, tan h paired with a bad initializer, a poor parameter initialization will hurt your accuracy a lot. And because of this, there's lots of activation functions, parameter initialization strategies that specifically attempt to fix problems with like tan h or things. So one example of this is there's Glorat initialization or Xavier initialization, which are actually the same thing. It was invented by Xavier Glorat, and some people use the first name, some people use the last name. But this is the, I'm trying to, I'll try to get this correct. I think it's the square root of n divided by 6, right? What was it? 6 divided by n. So then you initialize your parameters uniformly in this range, and you can kind of show that this is good for things like maintaining the scale of the inputs and outputs within NLPs or something like that. But I think the activation function will potentially make a significant difference, but TANH and ReLU are two good ones to try, and then you can try other ones if you want to try, if you feel adventurous. Okay, so now maybe I'll talk about the more interesting, a more interesting thing. It's a bit more advanced, but I think this is kind of the exciting, one of the exciting things that you can test out with that lets you incorporate a little bit of like linguistic knowledge or domain expertise into your models. In structured convolution, basically what it is language has structure. And we can use it to think about how we localize features or how we, calculate CNNs. So for example, if you want to do a classification of some sort of semantic task, what nouns interact with what verbs is probably an important thing to know. Like you might want to know like who did what to solve that task, right? But normal CNNs just look at local context windows. They might look at very broad context windows, but in order to do that, they need to be very, they don't do it in a very parameter efficient or intuitive way. So what a structured convolution could do is it could take into account some sort of structure, for example, dependency structure, in order to calculate interactions between words in a more intelligent way. And so one example of this is CBOW makes and repairs jet engines. So a dependency tree basically says that CBOW is the subject of makes, engines is the object of makes, and then jet is a noun modifier of engines, etc. So it tells you the relationships between all the words in the sentence. And there's a couple of ways that you can express this in an NLP-related model. So one way you can do this is by calculating paths through the tree and explicitly running convolutions over these paths. So if you have a word, M, you can take a step up the dependency tree up to its parent, and then take another step up the dependency tree to its grandparent, and then you define the convolution not over the three neighboring words, but rather the word itself, its parent, and its grandparent. So this allows you to calculate features from these using the standard, idea of having a convolution where you have the same function to calculate the features for all of these. And you can take a step up to the great-grandparent and the great-great-grandparent, etc. You could also do siblings. So if you take a step up and then take a step back down, you could calculate a convolution over all the siblings of a word. So that would be like if it's a noun, you take a step up to the verb and then you take a step back down. And you could potentially take a step up and look at the sibling, or take a step up and look at two siblings, or things like that as well. So basically what you do is you define what inputs you use to the convolution based on this dependency tree. Yeah.
So if you're traversing the independence comparison tree, then do you have to allow the convolution window size to change dynamically? Because if it's shallower in the tree, then you may not have a grandparent.
So do you have to allow the convolution window size to to change dynamically, because if you're in the top of the tree, you might not have a grandparent. And the answer is we do padding in wide convolutions, and that's the same thing that we would do here, I think. So you just pad the grandparent to be like a pad vector or something. Yeah.
So going padding, it means it may not be like at the start and end of the sentence when it falling down the tree into a sentence, there will be like padding in between the words.
No, I don't think that's exactly what this means here. Basically, you can think of another way to think of convolutions, like it said in the book, is basically you're stacking together vectors, and then you're feeding those into an NLP, right? So, like another way to think of a convolution is if you have 4 vectors, basically you're concatenating. These vectors. Sorry. I need an eraser. You're concatenating these into one big vector. You're concatenating these into one big vector. And you're concatenating these into one big vector. And then you're running all of these vectors through an NLP. So that's like the alternative view of convolutions that was talked about in the reading as well. So what you would be doing here is you would essentially be concatenating the vector of the word itself with the vector of its head, with the vector of its grandparent, and then running that through an NLP. And it's the same idea as a convolution, but maybe that's a more intuitive way to think about it within this framework. Does that answer the question? Or? Okay. So this is one way. I think this is a really interesting way, and I think it makes a lot of sense. I haven't seen as many people use this. I think one reason why people don't use this quite as much is it's a little bit more difficult to implement. That being said, I think it's a really good idea, so it might be worth trying if you want to do something related to this. Another way that's more popular and actually has been used relatively widely is graph convolution. And the idea behind graph convolution is basically whenever you have a link in the graph, according to that link, you multiply the vector by a weight matrix, and you feed it as input into the final function. So in this example, we have disputed, and we have the object link and the subject link. So when we calculate the feature vector for disputed here, we take the vector for lane, we multiply it by the W subject matrix. So this is a specific parameter matrix for subjects, and add it. We take disputed, we multiply it by the W self matrix, which is the matrix for the word itself, and add it. And then we take the vector for estimates, and we multiply it by the W object matrix, and you input it here. This is actually, now that I think about it, maybe these aren't so different. So yeah, I just thought about it now, and maybe these are not so different. But basically, essentially, when you did a graph convolution, like when you do something like this, you would essentially need to draw links between the word itself and its head and the word itself and its grandparent and label them appropriately. And you could probably express this type of thing as a graph convolution as well. So the only difference is, hang on one second, we'll get to that. So the main difference here is that in this work, for example, by Marchigiani et al., they're only looking at the immediate neighbors. And they're looking at all the immediate neighbors. They're considering the labels of the immediate neighbors within a convolution like this. And in this case, it's not looking at just immediate neighbors, but it's also looking at things that are 2 hops away. So yeah, the question.
So how do you actually get these graphs? Do you have to make them manually for each sentence?
So how do you get these graphs? That's a very good question. You would normally use a dependency parser, an automatic dependency parser, and we're going to talk about how to build one later. So if you feel really, really ambitious for your final project, you could build a dependency parser and then do graph convolution, but I would suggest you use an off-the-shelf one, because there are other people who have created them, and they work pretty well. So, Yeah.
When we're building these graphs, do we think of them as directed, or
Um,
are we thinking of them as directed graphs, or?
Are we thinking of them as directed graphs? Yes, we are. So basically, a dependency graph. So basically, a dependency graph has a thing pointing from makes to subject. So you see, this is directed.
Graph
But
convolution, we're using the same W subject for that.
actually, you aren't. So if you see here, we have W subject. So yeah, we have W subject prime and we have W subject. So that's depending on the arrow. So this is actually really important because, you know, a noun being a subject of the verb has very different meaning than the verb being, you know, having a noun as a subject. So, yeah. Oh, wow. I forgot I have a whole section left and we only have 2 minutes. So I think... I think I'll cover this next class. So let me skip this. This is very interesting. So I'll make sure I cover it. But let me skip this section. But what I do want to cover, and it's not dependent on the last section, is a case study. And this is convolutional networks for text classification. So this is a paper that you should probably read carefully and potentially implement as part of assignment 1. And basically the idea is it's pretty simple. It's convolutional neural networks that are used in text classification. It's essentially a single layer network. But one major thing that they have is they have convolutional filters of different widths. So they have convolutional filters for bigrams, for trigrams, for 4grams, for 5grams, et cetera. And so this allows you to pick out different types of features. They have dropout on the penultimate layer of the network. They try out with pre-trained or fine-tuned word vectors and use both in the end. And it had state-of-the-art or competitive results on sentence classification at the time. So I think it's not hard to implement compared to, you know, some of the other models we'll talk about in class, but it would be a very good place to start in practice. So, yeah, that's all I have for today. So.